let's record this. Okay, so now let's do a brief review of what we have learned so far in this chapter. Okay, so in this chapter, we are talking about the properties of a random sample. Okay, so in the first section, we discussed the concept of IID random variable or IID random sample. So meaning independent, identically distributed random variables. Okay, so based on this property, then the joint PDF or PMF of this IID random sample can be written as this product, the product of each individual PDF or PMF. Okay, and the form of this individual PDF or PMF is the same as the populational distribution. Okay, so this is the key property of IID random sample. Okay, and in the second section, okay, the second section, so we mainly talk about the property of the sample mean and sample variance. Okay, sample mean and sample variance. Okay, so we first talk about the definition of a statistic. So what is a statistic? Okay, so basically a statistic is a function calculated based on the random sample. Okay, so it should not contain the unknown parameter, the unknown populational parameters that we want to make inference about. Okay, and we mainly talk about the two statistics. So that is the sample mean and sample variance. So their definitions. Okay, okay, and of course the sample standard deviation is just the square root of the sample variance. Okay, and we also talk about the alternative formula to calculate this sample variance. Okay, okay, and the properties of the sample mean and sample variance. Okay, so that's a given in this lemma. Okay, and the next theorem. Okay, so basically this the expectation of sum, the expectation of variance of sum of functions of IID sample. So we can directly write this as the n multiply the individual expectation or variance of the function of individual random variable. Okay. And the next property of sample mean and the variance shows, okay, the expectation of sample mean and the expectation of sample variance is exactly the population mean and population variance. Okay, so in the language of next semester, so statistical inference, so the sample mean and the sample variance, so they are called the unbiased estimator of the population mean and population variance. Okay. And also we mentioned the variance of the sample mean is the population mean divided by n. N is the sample size, so number of observations in the random sample. Okay, so those are the properties of sample mean and sample variance. Okay, and we also mentioned the MGF technique for the sample mean. Okay, I'm the moment generating function method for the sample mean. Okay, so use this method, so we can. This method is useful to find out the distribution of a sample mean. Okay, so by comparing the form of the MGF, so we can see, okay, which is the distribution of the sample mean follows. Okay, and we also mentioned this convolution method, so which is basically the same as the Jacobian method, but now we write this. This is useful for find out the PDF of the sum of two independent random variables. So now we write this as a convolution formula. Okay, so basically this is the same as the Jacobian method. Okay, so so far in the in section 5.2, so this section, so here we do not have any distributional assumption for the population. Okay, so in other words, those results are general results, regardless of the distribution that the population follows, right? So we didn't say the population has to be a normal distribution. It can be any type of distribution. So those properties of the sample mean, okay, the sample mean and the sample variance. For example, they are unbiased estimator for the population mean and population variance. So this is a general result for any distribution. Okay, and in the next section, okay, so now we assume the population follows the normal distribution. Okay, so then that means that this random sample is from a normal distribution. Okay, and now we have some more specific results for the sample mean and sample variance. Okay, so so as I mentioned, so basically this can be summarized in 4 sentences. Okay, so the first one is the sample mean of a normal of a random sample from the normal distribution. So the sample mean follows a normal distribution. Okay, so that's the first result. Second is the sample variance follows a chi-squared distribution. Chi-squared distribution. Okay, up to some constant. So I didn't mention the constant part. So we have some constant like n-1 divided by sigma square. Okay, but you can remember this result just like the sample variance follows a chi-squared distribution. Okay, and the third sentence, third result is this quantity. Okay, so this is the ratio related to the sample mean and sample variance follows a t distribution, right? Okay, and the ratio of 2 independent sample variances like this follows a f distribution. Okay, so basically those are the 4 results related to the sample mean and sample variance from the normal distribution. Okay, okay, I think here I want to add a few comments about the t distribution and the f distribution. Okay, so this is just a kind of recall what we have learned in your introductory statistics course. Okay, so can you remember, so where have you seen this t distribution and the f distribution? So in the introductory statistics course. Okay, so here the t distribution, so I think you must have seen this. Okay, so here is we want to test the one sample t-test. We basically we want to test this hypothesis. So we have the random sample is from a normal distribution, and what we want to test is this. So the null hypothesis is the mean equals to some given number, let's say mu0. Okay, and the alternative is like this mu is not does not equals to this mu0, right? And I think in your introductory statistics course, so basically we need to construct this t statistic, right? The t statistic, so which is defined as this x bar minus mu0, okay, and divided by this s divided by square root of n, right? So this is called the t statistics, okay. And then under the null hypothesis, so this t statistics follows a student t distribution with n-1 degrees of freedom, right? And then we will look at the the quantile of this t distribution to see to find out the p-value, right? So if the p-value is less than 0.05, the commonly used threshold, so we will see we say this this test is significant, then we will reject null. So otherwise, we fail to reject the null hypothesis. Okay, so that is the t-test we learned, or more rigorously, we call it one sample t-test. Basically, we test the mean, right? Okay, so basically now we can see the corresponding underlying theory here. Okay, so why we use the t-distribution and call this t-test? Okay, because here what we learned here, so that is this quantity, okay, is following a t-distribution, okay, with n-1 degrees of freedom. Okay, so here in the note, I wrote down a more general result here. Okay, so like here, so if we have one random variable u from this standard normal distribution, okay, and the other one follows a chi-squared distribution with degrees of freedom p, okay, and if u and v are independent, okay, so then this statistic, so that is constructed as the ratio between u and v. So this follows a t distribution with degrees of freedom of p. Okay, so we will prove this soon. Okay, so let's just briefly review the results here. Okay, so basically this t distribution, so that is corresponding to the t-test, the one sample t-test in the applied statistics course. Okay, and then next the f distribution. Okay, so do you guys remember? So like, where have you seen this f distribution in the introductory course? F distribution. Okay, so here I think this is you must have seen this in the analysis of variance, ANOVA, right? ANOVA analysis of variance method. Okay, so what is ANOVA? So the basic ANOVA analysis of variance. Okay, you guys need to know this. Okay, this is basic. Okay, so like ANOVA, so basically we have more than 3 groups of continuous data, right? So like, for example, here we have 3 groups of data, okay? And then we want to compare if their means are equal, right? We want to compare the means of the more than 3 groups of data, okay? And then what we did in ANOVA is like, basically we partition the total variance, right? The total variance of the data. Okay, I will just briefly review this. Okay, the total variance of the data, or we say the total variation of data. So we basically write this total variation as the between group variance, like this, between the group variation, and plus the within group. So that means the variation within the group, those groups. Okay, basically we partition the total variation of all those data into the sum of between group plus the within group variations, right? Okay, and then we construct a F statistic. So which is this between group variation. So divided by the total number of group. So I will write the M here, right? Divided by this within group variation, divided by the total number of individuals in each group. So like this. So I will write N here, something like this. Okay, so you guys can double check details in your introductory statistics textbook. So like this. Okay, so basically we construct this ratio, the ratio of two variances, right? Okay, and we will see the value of this F statistic. Okay, so if this F is large, okay, so that means the between group variation is much larger than the within group variation. Okay, so then we will see this test is significant. So that means the variation between those groups are larger. So we will have evidence that their population means are different. Okay. Otherwise, if this F statistic is small, is very small, so that means this between group variation is equal or smaller than the within group variation. So then we will see this between group, or we say the population means among those groups are not quite different, right? So that is the basic idea of ANOVA. Okay, so now let's look at this, what we learned here. Okay, so here we are basically comparing this, the ratio of two sample variances. Okay, so now we know, okay, so this statistic, this quantity follows the F distribution. Okay, F distribution with, basically the F distribution has two degrees of freedom. So one is corresponding to the numerator. Okay, the other one is corresponding to the denominator. Okay, so this quantity follows the F distribution. Okay, and then as a general result here, so if we have two random variables follows from two chi-squared distributions, two independent chi-squared distributions. Okay, so then this ratio, okay, the ratio of the two chi-squared distributions follows a F distribution. Okay. Okay, and the F distribution has some interesting properties. Okay, so particular those two properties. So if this X follows a F distribution, so then the 1 over X follows F distribution. That is reversing the order of the two degrees of freedoms. Okay. Okay, so the other one, the other property, that is relating the T distribution to the F distribution. Okay, so if X follows the T distribution, so then X squared follows a F distribution. So the numerator degrees of freedom is 1. Okay, denominator degrees of freedom is Q, so which is the same as the T distribution. Okay, so basically that is the key results in this part. Okay, that is sample mean and sample variance from a normal distribution. Okay, so next we are going to derive on the next page. So I'm going to derive those key results. Okay, so which are using basically the results we learned in chapter 4, okay, about the bivariate and multivariate distributions. Okay, so but I think my plan is this. So first let's skip those, just leave it here. Okay, let's first move to the last topic, the order statistic. So after finishing the order statistic, so let's go back here, okay, and let's look at the derivations of those results. Okay, so now let's proceed to the order statistic, the last part. Okay, so did you guys all follow me here? Okay, so now let's start with the last topic, the order statistics. Okay, so here the order statistic, so that is basically statistics computed from the random sample. Okay, so now let's first look at the definition of order statistics. Okay, so basically they are like if here we have a random sample, okay, x1 to xn. Okay, so now we just sort them, okay, place them in a ascending order from the smallest one to the largest one. Okay, this random sample. Okay, and now we will put those numbers in brackets to denote the order of those values which are sorted in the ascending order, from the smallest one to the largest one. Okay, and the smallest one of them, so we will write this as x bracket 1. Okay, and the second smallest one, so we will write x bracket 2, and so on, right? And the largest one of them, so we will write x this bracket n. Okay, so we have this. Okay, so then this x1 to xn in brackets, so they are called the order statistics of a random sample. Okay, so here is so there are many statistics that is defined based on these order statistics. Okay, so the next definition so basically gives us a notation. Okay, so this notation b, so that when appearing in a subscript, so that is defined as the number b rounded to the nearest integer. Okay, so more precisely, so we can write this. So if the b is like in this range, okay, so here the I is basically the nearest integer to b. Okay, so then if we write b in this way, so that means we want to find the nearest integer of b. Okay, so like this. Okay, so this is just the notation for the content for what we want to introduce in the following part. Okay, so those are some statistics defined as a functions of order statistics. Okay, the order statistics. So first one is the sample range. Okay, the sample range. So by the name, so that is defined as the range of this random sample. So meaning the largest order statistic subtracts the smallest order statistic. So the largest one minus the smallest one. Okay, the second statistic, so that is called the sample median. The sample median. Okay, so I think we have seen the population median. Okay, the population median. So population median is like, okay, so if this is say the PDF of a distribution, so the population median means this value cuts the distribution, the probabilities of the distribution into two halves, right? So the probability of the values less than this population median is the probability of this part is 1/2, okay? And the probability of the random variable takes values greater than this median is also 1/2. Right? So that is the meaning of the median. Okay, so here the sample median. The sample median basically we cut the number of this random sample n into 2 halves. Okay, so that is defined this way. So if n is odd, then the median will just the order statistic in the middle one, right? So then half of the sample is less than the median, and the other half number of this random variable in this sample is greater than the median. Okay, so if n is even, so we will take the average of the middle two order statistics as the sample median. So in this way, still, half number of these random variables in this sample is less than the median, and the other half number of the random variables in the sample is greater than the median. Okay. So next one is called the 100 piece sample percentile. Okay, so basically we call this percentile. Okay, so the definition, the formal definition. So if we write in the numbers, so that is defined in this way. Okay, so that is the x np. So remember this. We put in this brackets in this way. So that means we take the nearest number of np. Okay. So if the p is in this range, okay, and then this percentile is defined this way. So if the p is in this range, okay. So the meaning of this is basically, so that is the observation such that approximately np of the observations are less than this observation. Okay, so p basically here is a proportion. Okay, so this percentile means the 100 p sample percentile means, okay, so n multiply p, this number of observations in the random sample are less than this observation. Okay, and the rest n multiply 1 minus p of the observations are greater than this observation. Okay, so this observation means this 100 piece percentile. Okay. Okay, so the next one, so based on this percentile, okay, so then we can basically divide say we have the number of sample, this random sample. So we can divide this random sample into 4 parts using 3 cutoff. Okay, so the first one is the median. So that is the middle part. Okay, the median. Okay, all based on this definition, the median is also the 50th percentile. Okay, the median, which is the 50th percentile. Okay, because that means the 50% of the observations are less than the median. Okay, and the rest 50th of the observations are greater than the median. Okay, so then the median is also called the 50th percentile. Okay, and then we can also divide the 2 parts, okay, into another 2 parts. Okay, so total 4 parts, divided the total number of random samples into 4 parts. Okay, so this one is called the lower quartile. So quartile, so I think quartile means the 4 parts, right? Okay, so that is the QL, so which is the 25th percentile. Okay, so this is the lower quartile, so which is the 25th percentile. Okay, so and similarly, so we have the upper quartile. Okay, upper quartile. So that is the 75th percentile. Okay. th percentile. Okay. So basically those 3 values, or we say 3 statistics, the median, the lower quartile, and the upper quartile. So they divided the whole random sample into 4 equally spaced parts. Okay. And we have another statistic, so that is called the interquartile range. Okay. So that is the range between the lower quartile and the upper quartile, so which is called the IQR, okay, the interquartile range. Okay, so basically those statistics, so they are defined based on the order statistics, okay, and then they provide the position of the center, okay, or the distribution of this random sample. Okay, so I think they are easy to understand. Okay, so next I'm going to introduce two important results about the distribution of the order statistics. Okay, so we know the definition of order statistics. So now we want to ask, how can we find the distribution of the order statistics? Okay, so the first one is about the distribution of a single order statistic xj. Okay, so here the xj means the jth order statistic. Okay, so we have this theorem. Okay, so here the x1 to xn denote the order statistics of a random sample, x1 to xn. Okay, so here we assume x1 to xn, this random sample is from a continuous population with the CDF capital F and the PDF small fx. Okay, so then we have this formula for the PDF of xj. Okay, so here the xj, as I mentioned, so that is the jth order statistic. Okay, so let's look at the form of this formula. Okay, so first we have this combinatory, these factorial numbers like this. Okay, so then we have this, the fx, capital Fx, so that is the CDF to the power of j minus 1. Okay, multiply the PDF of Fx, the PDF Fx, small f here. This is the PDF. Okay, and then multiply the third part, so that is 1 minus capital F to the power of n minus j. Okay, so here I have a heuristic derivation of this formula. So why we have the PDF of xj takes this form. Okay, so here we have a heuristic derivation. So meaning it is not quite rigorous, but based on some experience, okay, some intuition. Okay, so that means heuristic derivation. Okay, so let's think about this problem in this way. Okay, we want to find the distribution of xj, the jth order statistic. Okay, so I'm going to scan all the lecture notes with my writings and upload to D2L. So that means if you cannot follow me on everything, that is fine. Okay, you can look at this later after I upload this. Okay, but now let's focus on the idea here. Okay, make sure you understand the idea. Okay, so here let's see this. Okay, so if we are given a value small x, okay, so what we want to find is this, right? So that is this xj. So the PDF of this is defined as this. Let's first look at the probability of this. So that is this xj. Oh, sorry. Let's see this. So that is defined. The PDF is defined as this xj equals to a value, to a given value of x. Right. So it's like this. Okay. So here this PDF of xj. So basically, we can view this as the probability that the j's largest observation is close to x. It's close to x, right? So this is the definition of this PDF, right? So if you look at the definition of PDF, okay. So now we are going to divide this random sample. So contains x1 to xn. Okay, those n observations. We can divide this into 3 groups. Okay, into 3 classes. Okay, so here this small x, right? So this small x means a given value for the jth order statistic, right? This small x. Okay, so based on this, we divide by those n observations in this random sample into 3 classes. So the first one is those observations that are less than, this is less than x. Okay, here small x means a given value for the jth order statistic, right? So because the xj is the jth order statistic, so then in these n observations, there must be j minus 1 observations less than the jth order statistic, right? So in this class, we have j minus 1 observations. Okay, so here I write this capital X so to denote the number of observations in this random sample. Okay, so the second class, so those are the observations that are roughly equal to the given value of the jth order statistic. Okay, so here we have only one observation, right? So that is basically the xj, the jth order statistic. Okay, and the third group, we have the third group, which are the observations that are greater than this given value of the jth order statistic. So here we have n minus j observations, right? So this is just based on the definition of the jth order statistic, because it is the jth largest one. Oh, sorry, I say the reverse. Jth smallest one, the jth smallest observation, right? Okay, so that is the number of observations greater or equal or greater than this jth order statistic. Okay, and now let's look at this probability. Okay, this probability. Okay, so here we want to find this probability that the jth order statistic is greater than x, but less than x plus dx. Okay, so here the dx is just a very small interval, okay, beyond the given value x. Okay, I think based on the idea in calculus, you have seen similar symbols. Okay, so that means this j dx is just a very small interval beyond the x here. So it's like this. Okay, so now this probability, so basically based on the 3 classes so we just discussed, so this probability can be calculated in this way. Okay, so first, so basically the jth order statistic, so that is we have only one observation here. Okay, but here for this class less than x and the third class greater than x, so we have j minus 1 observations. Okay, so total number of combinations in this class is j minus 1 factorial. Okay, so here we can exchange the order of those observations as long as we have j minus 1 observations, right? And which is similar for the third class. So as long as we have n minus j observations in this class, the order doesn't matter. Okay, so those are in the denominators, so basically j minus 1 factorial multiply n minus j factorial. So those are corresponding to the number of combinations in these two classes. Okay, so now in the numerator, so we have n factorial. Okay, so that is the total number of total number of permutations, total number of ways we can order those n observations. Okay, so in other words, this is this constant part, this factorial part, correspond to the total number of combinations so we have for these arrangements. So that means we have the one observation corresponding to the j's order statistic. Okay, and the j minus 1 observations should be less than xj. Okay, and the rest n minus j observations should be greater than xj. So this corresponds to the number of the arrangements of this. Okay, and now, by the way, now can you see what distribution is this similar to? Right, actually this is similar to the binomial distribution. So the difference is now we have fixed a single observation here. Okay, so now we need to multiply the probabilities corresponding to each class. Right, so actually this is similar to the binomial distribution. So we learned before. Okay, so here we have j minus 1 observations need to be less than x. Right, so then the probability of x less than observations less than x, right? So that is based on the definition of the CDF, right? The CDF is this, the capital X less than or equal to small x, right? And we have j minus 1 observations corresponding to this group. Okay, so then here we multiply the CDF of x to the power of j minus 1. Okay, and then for the second class, so that is this one observation that is close to the given value. Okay, so that is the PDF of x multiply the length of this small interval dx. Right, so this part corresponding to the second class, so which is correspond to the single observation close to this given value. Okay, and the probability corresponding to the third class, right? So that is those observations need to be greater than x, right? So that is 1 minus the CDF to the power of n minus j. Okay, so this is the based on the definition of the j's order statistic. So we have this. Okay, so now we just move this dx, this small interval, into the denominator of this. So we write the formula in this way. Okay, so if you look at this, so now we let this small interval dx goes to 0 to make this as small as possible to make this dx. Okay, so then this is exactly the definition of the PDF, right? This probability divided by this small interval, right? So this is the density function. Okay, so then we have derived this formula for this PDF of xj. Okay, so do you guys follow the idea here? Okay, any questions for this? Okay, so basically this formula contains these factorial numbers. So those are the way to arrange those observations. Okay, and then we have the 3 probabilities corresponding to the probabilities for those 3 classes. Okay, so that is the distribution of the j's of order statistic. Okay, so this is the PDF of a single order statistic. So the next one, so we are going to discuss the joint PDF of two order statistic. Okay, so now we have two order statistics, xi and xj. Okay, and how can we find the joint PDF of them, of those two order statistics? Okay, so here we use a similar idea as the previous one. Okay, as the previous one. So previous one we have a single order statistic, which divided by the total number of observations into three groups. Okay, so now we have two order statistics. So then we can divide the total number of observations into 5 groups. Okay, so the idea is similar. Okay, the only thing is the calculation is a little bit complicated because we have more classes here. Okay, so here, so we have the u and the v. So u and v are the specific given values for xi and xj. Okay, so then the joint density function of xi and xj, so they can be interpreted as the probability that the ith largest observation is close to u. Okay, and the jth, this is largest. The jth largest observation is close to v. Okay, so now based on xi and xj, so we can divide the total number of observations in the sample into 5 classes. Okay, so the first class is those observations have value less than u. Okay, so less than xi. Okay, so second class is x that have values near u. Okay, so that is correspond to xi. So we have just a single observation here. Okay, so third class is those observations have values greater than u, but less than v. So between xi and xj. Okay, so then we have this number of observations, j minus I minus 1. Okay, and the fourth group, so those are observations that have value near v. So that is correspond to xj. So we have a single observation here. Okay, so the last group, so those are observations have values greater than v. Okay, greater than the xj. So we have n minus j observations. Okay, so similarly as before, so we can derive this probability. Okay, derive this probability. Okay, so now we have still the total number of the arrangements of the n observations, so that is n factorial. Okay, n factorial. Okay, and the number of permutation or arrangements for the first class, so that is I minus 1 factorial. Okay, so for the second class, we have a single observation. So there is only one way to, for the arrangements in this class. Okay, for the third class, so this is the number of observations in the third class. Okay, so in total, we have j minus I minus 1 factorial ways to arrange the observations in this class. Okay, and similarly for the last one. Okay, so n minus j factorial ways to arrange the observations in the last class. Okay, so now we need to multiply the probability. Okay, the probability. Okay, so for the first class, okay, so we have the probability of x less than u to the power of I minus 1. Right, so that is represented by the CDF. Okay, so x less than u. Okay, so that is for the class 1. Okay, so for the second class, that is this single observation close to U. Okay, so we write this as the PDF multiply this small interval du. Okay, so that is for the second class. Okay, for the third class, between U and V. Okay, so the probability of that is given by Fv minus Fu to the power of j minus I minus 1. Okay, so this is correspond to the probabilities of the third class. Okay, so for the fourth class observation, a single observation that is close to V. So we write this as Fv multiplied the small interval dv. So this is correspond to the fourth class. Okay, and lastly, the last class, so that is 1 minus the CDF to the power of n minus j. Okay, so that this is correspond to the probability of the the fifth class. Okay, and then now the next we just can move this small interval du and dv to the denominator of this probability. Excuse me. So then, based on the definition of the PDF, the joint PDF, okay, so we will have this. Okay. So then this is the formula for the joint distribution of xi and xj. Okay, so basically we have 5 classes, right? So this is the first one, second one, the third one. So between U and V, okay, and this is the for the fourth classes. Okay, and this is for the fifth class of observations. Okay, and still let's see this is actually this type of probability distribution. So that is similar to the multinomial distribution. Okay, so basically the difference is although we have 5 classes, okay, but the third class, okay, the second class and the fourth class, they have only one single observation. So that is kind of fixed, this number, okay. But the other 3 classes, so we have this number of combinations, okay. So then this is very similar to a multinomial distribution with 3 classes. Okay, and previously for the single distribution of single order statistic, so as I mentioned, so we have this second class have only a single observation, so that one is fixed. But for the first and the third class, so we have kind of a binomial distribution, to arrange those number of ways for those 2 classes. Okay, so that is the basically the distribution of a single observation order statistic and the joint PDF of a pair of order statistic. Okay, and finally we have this result. Okay, so that is the joint PDF of the total number of n order statistic. Okay, so actually this one is given in this way. So that is the n factorial. Okay, multiply the the joint PDF of the observations of this random sample x1 to xn. Okay, and because x1 to xn, so they are IID, so their joint PDF can be written as this product of individual PDF, like in this way. Okay, so the meaning of this is, so here we have the n order statistics. Okay, so basically we can think about this as the different ways, okay, different ways of order those n order statistics. Okay, so then the total number of ways to order them, so that is n factorial. Okay, and then we have n classes for the corresponding to those n order statistics, and each of those n classes, we will have one single observation correspond to the each individual order statistic. Okay, so which are given, the probability are given as fx1, fx2 up to fxn. Okay, but the total number of ways to arrange those n classes, so we have n factorial. Okay, so then the joint PDF of this n order statistic is given in this way. Okay. Okay, so those are the three results, okay, for the order statistics. Okay, so are there any questions, okay, about them? Okay, no, okay, that's good. Okay. So here I want to ask a question here. Okay, so here to find the, I would say, the closed form of the PDF, either for a single order statistic or a pair of order statistics, or the joint PDF of all the n order statistic. Oh, I would say this. So what I mean is this. Okay, to find the closed form of the first two. Okay, so meaning the PDF of a single order statistic and the pair of these two order statistics. So what we need is the closed form of the PDF, so small f. We also need the closed form of the CDF. Right, so we will need the closed form expression for the PDF and the CDF. Okay, so actually this is only feasible for a small number of distributions. Okay, because there are many distributions do not have a closed form CDF. Right? Yeah. Okay, so I mean, for manually calculation, so we have to know the closed form of the PDF and the CDF. Okay. But I would say these two formulas are still useful, to find out the distribution of order statistics. Okay. Because I mean, even for those distributions do not have a closed form CDF, we can use the computer simulation, to give us the empirical form of the CDF. Okay, so in other words, we can simulate the CDF. Okay, and then we still can use those formulas to find out the distribution of the order statistics. Okay, so this is, of course, the computer simulation, so that is beyond our course. Okay, here what I'm saying is, so those two formulas are required. Okay, so but usually this, to get the closed form expression of the PDF of the order statistic, so we we have only a small number of simple distributions which are feasible to do this. Okay, so that means we need both the closed form CDF and PDF. Okay, so now let's look at the some examples. Okay, so as what I just mentioned, okay, how can we use those formulas to find out the PDF of the other statistics? Okay, so the first one is so we have the only 4 observations, x1 to x4. So this random sample is from the exponential distribution. Okay, the parameter is 1 for this exponential distribution. Okay, so now let's find the joint distribution of the other statistics, x1 to x4, the joint distribution of those 4 other statistics. Okay, so this one we can directly apply the formula for the joint PDF of all the n observations. So here n is 4. Okay, so that is the total number of arrangements. So that is 4 factorial. Okay, multiply the individual PDF. Okay, so which is here. Again, okay, we need to put the support here. Okay, we need to be clear about the support. So here, those small x1 to x4, those letters corresponding to the given value of the other statistics, x1 to x4. So they have this relationship. Okay, so that is x1 less than x2, and so on, less than x4. Okay, so this is the support. Okay, so next example. Okay, so here this random sample is from this uniform distribution on a range from 0 to 1. Okay, so now we want to show the jth order statistic follows a beta distribution. Okay, so we need to find out the PDF of the jth order statistic. Okay, so for uniform distribution, so in chapter 3, we already know the PDF is 1 divided by the interval, so which is 1 here. So the PDF is just 1. Okay, the CDF is just x. Okay, and the support is from 0 to 1. Okay, so now let's find out the PDF of the jth order statistic. Okay, so here we have a closed form CDF and PDF for the uniform distribution. So now we can directly apply the formula. So we just learned. Okay, so those factorial numbers are the total number of arrangements for the 3 classes, right? Okay, and multiply the CDF to the power of j minus 1 correspond to class 1. So observations less than the jth order statistic. Okay, multiply the PDF. Okay, and multiply the probabilities corresponding to the 3rd class. So 1 minus the CDF to the power of n minus j. So those are the probabilities corresponding to the 3rd class. Okay, and then after some simple algebra, okay, so let's try to put the x to the power of j minus 1 in this way. Okay, and then 1 minus x. So I will just write this follows the form of the beta PDF. So we have n minus j plus 1 minus 1. Okay, and then those factorial numbers, so we learned in chapter 3. So they can be written as this gamma function, right? So gamma function of n plus 1. So that is equals to n factorial. Okay, and then same for the denominator. Okay, so we have gamma j, so that is j minus 1 factorial. Okay, so remember this, the gamma function of n, so that equals to n minus 1 factorial. So when n is an integer, right? So we have this definition for gamma function. Okay. Okay. So then this is what? This is exactly the beta distribution, right? So we learned in chapter 3. So beta distribution, its support is between 0 and 1. Okay. The form of the PDF is this. Okay. So that is about this example. Okay. So the next one. So here we have the random sample x1 to xn. IID random sample from this uniform distribution. Okay. So here let x1 to xn denote their order statistics. Okay. So now let's find the distribution of the range R, and the mid-range V. Okay. So here the range is the largest order statistic, subtracts the smallest one. Okay. And the V, so V is defined by the average of x1 plus xn. Okay. So the middle of the largest one plus the smallest one. Okay. So now let's find the distribution of R and V. Okay, so here the R and V, so they are the functions of x1 and xn. Okay, so then our idea is we first find the disjoint distribution of x1 and xn. Okay, so this is our idea. Okay, and the next, we will just use the Jacobian method. Okay, because R and V, so they are linear transformations of x1 and xn. So we are going to apply the Jacobian method to find out the joint PDF of R and V. Okay, and then finally, we will just integrate out R and V to find their corresponding marginal PDFs. Okay, so that's the basic idea. Okay, so here we already have the closed form PDF and CDF for the uniform distribution. Okay, so then we can directly apply the formula. Okay, to find out the joint PDF of x1 and xn. Okay, so here I will leave the more detailed calculation for yourself. Okay, so here, this is the joint PDF of x1 and xn. Okay, and second is now we are going to apply the Jacobian method. Okay, so here based on this linear transformation between RV and x1, xn. Okay, so then we can solve x1 and xn using V and R. Okay, so we have this. Okay, and then we based on the support of x1 and xn. So remember x1 and xn, they have this relationship because they are order statistic. So it's in this range 0 and 1, and x1 need to be less than xn. Okay, so using this, so we can put this R and V into this inequality. Okay, to find out the support of R and V. Okay, so which is this one. Okay, by this inequality for x1 and xn, so we can plug in the solution of V and R into these inequalities and then solve for V and R. So we have the support for R and V here. Okay, and of course we need to evaluate the Jacobian. Okay, so here that is -1, just -1. Okay, so then we have everything. So we can plug in the values. Okay, plug in the values of x1 and xn into the joint PDF to get the joint PDF of R and V. Okay, so which is here. Okay, Okay, and finally, now to find the marginal PDF of R, so we need to integrate out V. Okay. Okay, and similarly to find out the marginal PDF of V. Okay, so now we need to integrate out R. Okay, so that is the about this question. Okay, so that is all about the order statistic. Okay, so are there any questions? Okay, so basically, for this order statistic, so you will need to know basically the results about the PDF of a single order statistic and the joint distribution of a pair of order statistic. Okay, you don't need to memorize the exact form. Okay, so I will provide this in the formula sheet in the exam. Okay, but I will like in the midterm exam, so I will directly give you this formula, but I will not explain what exactly each component in the formula. Okay, so that is the requirement for the exam. Okay, so you need to understand the meaning of this formula. Okay, so that is all about the order statistics. Okay, so now let's turn to the last part. Okay, so the derivations of the distributions for the sample mean and sample variance of a normal distribution. Okay, of a normal distribution. Okay, so first let's look at this theorem 5.3.1. Okay, so here basically it has three parts. First is X bar and the sample mean and sample variance are independent. Okay. The second part, X bar, follows a normal distribution. Okay. So as I mentioned, we already shown this previously using the MGF technique. Okay. And the third one is this sample variance has a chi-square distribution. Okay. So now let's show part A and part C. Okay, part A and part C. Okay. So here what we are going to use is the method in chapter 4. Okay. So to show X bar and S square are independent. Okay. So now we want to write this X bar and S square as functions of independent random vectors. Okay, so we know the functions of only random factors, so they are independent. Okay, so now first we are going to write this S square in this way. Okay, so this is the definition of S square. Okay, so again, probably you don't have time to write everything. So here still try to understand the idea, and I will upload this to D2L after the class. Okay, so now basically we want to write the S square in this way. Okay, so here we have the sum of n square terms. Okay, so now we write the first one as x1 minus x bar square. Okay, and the other n minus 1 terms, okay, from the I equals 2 to n. Okay, we separate them in this way. Okay, and now here we just put the second term here. Okay, and now we want to do some manipulation for the first term. Okay, for the first term. Okay, So here for the first term, this is a square term. This is square. Okay, so then first we can change the sign inside this square term, right? So here we write put a minus sign here because this square, it doesn't matter to change the sign, right? So here we have minus x1 plus x bar. Okay, here we just change the sign inside this square. Okay, and then here we will add the sum of xi and minus n x bar. So basically they are the same. We didn't change anything here, right? Okay, so basically this is just a 0. Okay, and then for the square term we just change the sign. Okay, so this is the same as above. Okay, so now we are going to do this. Okay, so here we have the let's see this one. This one we will put this, the sum of x1 to xn. We subtract x1, right? So then here we have this. So that is I is from 2 to n, the sum of x2 to xn here. Okay, and then here for the x bar term, so we have this n minus 1 x bar. Okay, so that is from here to here. Okay, so this term is still the same as above. Okay, and now for this one, okay, let's still look at this second term. Okay, so this second term here we have a summation of n minus 1 observations. So from x2 to xn, right? And here we have n minus 1 x bars. Okay, so then we will give each n minus x bar to the first summation. Okay, so that is xi minus x bar, right? So we have this summation is from I to n. Okay, so we have a square here. Okay, so you may wonder why we want to spend time to write this s square as this form. Okay, so now we can see our goal is actually this. So here the s square sample mean can be written as a function of only this. So x2 minus x bar, x3 minus x bar, up to xn minus x bar. Right? So this s square is a function of these random variables. Okay, after we do this. Okay, so next we are going to show, okay, these random variables. So this one. Okay, all these random variables, so they are independent of x bar. Okay, all those random variables, x2 minus x bar, are independent of x bar. Okay, and then so on. All those random variables are independent of x bar. Okay, so first to show this, we have a way to simplify the calculation. So it's like this. Okay, so here we can see the xi minus x bar. So we are calculating this for this general normal distribution with mean mu and the sigma square. Okay, but this calculation, so we can simplify this to the standard normal distribution based on z. Okay, so remember we have that formula for location scale family, right? So this is we can write this as a scale parameter mu sigma multiplied zi minus z bar. So here the z are random sample from the standard normal distribution. Okay, so here then this xi minus x bar and the zi minus z bar, so they are one-to-one functions. So just up to this scale parameter sigma. Okay, so then what we want to show is those xi from 2 to n minus x bar. So they are independent of x bar. So then here, because this one-to-one relationship, it is sufficient to show those functions based on z. So they are independent of z bar. Okay, so those z's are from the standard normal distribution. Okay, so did you follow the idea, the logic here? Okay, so here we just need to show this. So based on the standard normal distributions. Okay, so here in the following calculation, so I'm still write the z's as x. Okay, it's kind of an abuse of notations. I will still write the z's as x. Okay, but note they are now from the normal, from this standard normal distribution now. Okay, so here we need to use this oh, sorry. Yeah, this is the page. I switched the order of the page. Sorry. Mess up. Okay. So here, okay, remember we want to show this. So those values, so they are independent of x bar, right? So the idea is this: s is a function of those variables, right? So we have shown this. Okay, and now we want to show those random variables are independent of x bar. Okay, and because s squared are functions of them, so then s squared is independent of x bar. Okay, so now we want to show these random variables are independent of x bar. Okay, so the idea is we want to use the factorization theorem in chapter 4. Okay, so first let's look at the joint PDF of this random sample x1 to xn. The joint PDF. Okay, so basically, remember here we assume x1 and xn, so they are from the standard normal distribution. Okay, so then the joint PDF is just the product of the n standard normal PDFs. Okay, so which is this? So here I already put the n in this constant and the n, the sum of xi in this exponential term. So that is the joint PDF of x1 to xn. Okay, and now we want to make this transformation. Okay, make this transformation. Okay, so here the y1 is just the x bar. Okay, and the y2 to yn. Y2 to yn equals those random variables. So we want to show they are independent of x bar. Okay, so we make this type of transformation. Okay, so now what the goal is this. So we want to, based on the joint PDF of this random sample, make this transformation and find the joint PDF of this transformed variables y1 to yn, and then use the factorization theorem, to see if this joint PDF of the new random variables can be factorized as a function of only x bar and another function of only y2 to yn. So then we are done, right? Based on the factorization theorem. Okay, so now let's continue with the transformation using the Jacobian method. Okay, to find the joint PDF of y1 to yn. Okay, so this is just a simple linear transformation between x and y. Okay, so then we can easily solve for x1 to xn using y1 to yn. Okay, so here is the solution. Okay, so this is just the linear one-to-one transformation between x1 to between x and y. Okay, so then let's apply the Jacobian method to find out the joint PDF of y1 to yn. Okay, so then what is the Jacobian? Okay, so actually you don't need to write out, you don't need to find the exact value of this Jacobian. Okay, so what you need to know is because this is a linear one-to-one transformation. Okay, so then here, like, in the first row, we need to take, for example, die x1, die y1, right? Die x1, die y2, okay, and so on. So all of them are basically constant, like this way. Okay, so if you just write down the Jacobian, so you will see this. Okay, so actually the value of this Jacobian determinant of the Jacobian matrix is n. Okay, but even if you think this is complicated, so you will just write this as a constant c, as a number. Okay, a constant number c. Okay, so it actually does not affect our proof, the following proof. Okay, so here, then now let's apply this Jacobian method now. Okay, so here the joint PDF of y, so that is this Jacobian determinant of the Jacobian. Okay, multiply this joint PDF of those original variables x1 to xn. But now we plug in this solution for x1 to xn with y1 to yn now. Okay, so this is just we plug in the x1 to xn into the PDF of x. Okay, so we have this. So this is the joint PDF of y1 to yn. Okay. So here, so now we just need to do, what we want to do is, we want to write this joint PDF into two parts. Okay, so the first part is contains only y1. Okay, and the other part contains the rest terms. So that is from y2 to yn. Okay, so I will leave this. This just needs a little bit algebra here. Okay, to expand those square terms. Okay, and then put those terms of y1 together. Okay, and then put the other terms contains y2 up to yn together. So then you will see this. Okay, this joint PDF can be factorized as the products of two terms. Okay, first one contains only y1. Okay, second one contains y2 to yn. Okay, and then up to a constant c. So the constant c now corresponds to this constant part. Okay, so then from here now we can see, okay, so the y1 are independent of the rest variables from y2 to yn. Okay, so then this is what we want to show. Okay, so y1 is x bar. Okay, and y2 to yn is this x2 minus x up to xn minus x bar. Okay, so then we have shown this x bar are independent of those terms, those random variables. So then, as we have shown before, so the sample variance are functions of only those terms, those random variables. Okay, so then this s squared are independent of x bar. Okay, so did you guys follow the basic idea here? Okay, so here the kind of the idea is, so first we need to write this s squared as the function of those n minus 1 terms. So those terms are kicking off the first x1. Okay, we write this from x2 to xn. Okay, and then we want to show this, those terms are independent of x bar. Okay, and how to show they are independent? So this is just the application of the Jacobian method. We first write the joint PDF, okay, and make this transformation. Okay, and then we can find out the joint PDF of y1 to yn. And then just after some algebra, so we can see this joint PDF can be factorized as two parts. Okay, and then by the factorization theorem, we will see the y1 and the other y's are independent. Okay. Okay, so this is the for part A. This is for part A. Okay, and now let's look at part C. Okay, so part C is basically saying this sample variance after this normalization follows a chi-squared n-1 distribution. Okay. Okay, so here, first, let's still, there is a way to just simplify the calculation. So based on the standard normal distribution. Okay, so here we have this S squared. So this S squared is calculated from a general normal distribution with mean mu and the variance sigma squared. Okay, so here the S squared up to this constant part sigma squared multiply the SG squared. So here the SG is the sample variance from a standard normal distribution. So it's only up to this constant sigma, okay, to sigma squared up compared to S squared, right? So then if we put this SG here, okay, so then this quantity becomes n-1 multiply SG squared. So again, SG is the sample variance from the standard normal distribution. Okay, so then again, it is sufficient to show this for the standard normal. Okay, so basically this is a kind of technique. So we already seen in chapter 3, right? To find out the mean and the variance of a normal. So we start with the standard normal. Okay, so similar, we use the same technique here. Okay, so here the idea is, so here the SC is the sample variance for n observations, right? x1 to xn, and they are from the standard normal distribution. Okay, so here our idea is we want to prove this using the mathematical induction, method. Okay, so it's like this. So here we define this sequence of sample variance. Okay, so here the Sn squared. So this is the sample variance for the n observation. So x1 to xn. Okay, and then S, the subscript is n-1. Okay, so that means the sample variance for x1 to xn-1. Okay, so that is for the first n-1 observations. Okay, and then so on. We have the S2 square. So S2 square is just the sample variance of the first two observations, x1 and x2. Okay, so here to use the mathematical induction, okay, so it basically contains two steps, right? So first we need to show for n equals 2. So this relationship is true. So that is this one. This quantity follows the chi-square 1 distribution, right? So that is for n equals 2. Okay, and then we need to assume for n equals k. Okay, then to show this is also true for k plus 1, right? So that this is the mathematical induction method, right? Okay, so now let's see the more details about how to show this. Okay, so first, because we are using this induction method, so we need to find out a relationship, an inductive relationship between Sn and Sn minus 1, Sn square and Sn minus 1 square. Okay, so that is the sample variance for the n observation and the sample variance for the n minus 1 observations. Okay, so this one, this is not hard to find this relationship. Okay, so I will leave this as a homework exercise. This is one of your homework problem to find out this relationship between Sn squared and Sn minus 1 squared. Okay, it has this relationship. Okay, now let's go to the mathematical induction method. So first we need to show for n equals 2. Okay, so as this quantity follows a chi-square 1 distribution. Let's see how can we show this. Okay, so here for n equals 2, okay, so by this formula, okay, so we put this formula as this number with this number. Okay, so here the n equals 2, so then we have this S2 squared. Okay, so we just plug in the n equals 2 in this formula. Okay, so then we have S2 is this quantity. Okay, so now we have only 2 observations, right, when n equals 2. So that is x2 and x1. So we have this. Okay, now let's see this. So we know the x1 from this standard normal and x2 also from the standard normal. Okay, and then they are IID, so meaning they are independent, right? Okay, so then we have a result for the normal distribution. So the difference of 2 normal random variables, if they are independent, okay, so then the difference of them also follows a normal distribution, right? And the mean of this difference is the difference of the 2 means, right? And the variance, so the variance is the sum of the 2 variances, right? So then we have this x2 minus x1 follows a normal distribution, okay, with mean 0 and the variance is 1 plus 1, so which is 2. Okay, so in other words, we have this. Okay, so now we standardize this x2 minus x1 divided by their standard deviation. So then this follows a standard normal distribution. Okay, and then in the we mentioned in the lemma here. Okay, here we have if z is a standard normal random variable, so the square of this standard normal follows a chi-square 1 distribution, right? So then now we just square this standard normal distribution. Okay, so this follows the chi-square 1 distribution, okay, by the lemma we just mentioned. Okay, so then this is exactly the S2. Okay, so then we have shown this for n equals 2. Okay, so in other words, the sample variance of the first 2 observations, S2 squared, follows a chi-square 1 distribution. Okay, so now by using this mathematical induction, so now the next step is we assume for when n equals k, so then this will hold. Okay, so that is n, we just replace n with k, right? So that is k minus 1 multiply sk squared follows the chi-square distribution with k minus 1 degrees of freedom. Okay, so we need to show this is true for n equals k plus 1. Okay, so now we assume when n equals k, this is true. We also need to show this is true for n equals k plus 1. Okay, so again, for n equals k plus 1, again, we need to use this induction relationship. Okay, so that is by this, so we have, now we plug in n equals k plus 1, right? So then we have this k multiply sk plus 1 squared, okay, equals this term plus this term. Okay. So now what we want to show is this. Okay, so here the first term, this k minus 1 as k squared. So we know, we already assume this follows the chi-square k minus 1 distribution, right? And then we want to show the second term, so this one. This one follows the chi-square 1 distribution. Okay, and then this also independent of the first term as k squared. Okay, so then by the part B, okay, we have this result for chi-square distribution. By part B of this lemma, okay, so the sum of independent chi-square distribution also follows the chi-square distribution. So the degrees of freedom is sum of them. Okay, so then if we can show this, the second term also follows the chi-square distribution, and it is independent of the first term. Okay, so the sum of two independent chi-square distribution is also a chi-square distribution. Okay, so then we are done, right? Okay, so it's this. Okay, so now let's see how can we show the second term follows a chi-square distribution. Okay, so our reason is this. So first, all those xi's, so they are independent. They are IID, right? So then this, we have this, the xk plus 1. So it is, of course, independent of all the other k observations. So they are independent. Okay, so here, then we have this. Here, the sk square. So remember, sk square means the sample variance of the first k observations of x1 and x2 up to xk. So sk square is a function of only x1 to xk, right? So then this one, the xk plus 1 is independent of sk square. Okay, so then actually we let's see what is this. Okay, so that is the first step. Okay, so the second thing is this. So we also know the sk square is independent of xk bar. Okay, so that is the result we just shown, right? So that is the sample variance is independent of sample mean. Okay, so this is a important result. So we just shown that, right? From the part A of this theorem. Okay, so now let's see this. So now we can see sk square. So here, the first term and the second term, so they are independent, right? Because the second term is a function of xk plus 1 and x bar. Okay, and we have shown, okay, xk plus 1. So this is independent of sk square. Okay, and then here the xk bar, the sample mean. So it is also independent of the sample variance sk square, right? So then we have this, the first and the second term, so they are independent. Okay, so then we have finished this part, so they are independent. Okay, so next we want to show this, the second term follows a chi-square 1 distribution. Okay, so then how to show that? Okay, so again, this is by the property of the normal distribution. Okay, so as we can see, so this second term contains the xk plus 1, so which is from this standard normal distribution. Okay, and then the second term is xk bar. So we know the sample, this is the sample mean of a normal distribution, also follows a normal distribution. So mean is the same as the population mean. And the sample variance is the variance 1. So remember, this is standard normal, divided by the number of observations, so which is k. Okay, so then this xk bar also follows a normal distribution. Okay, and we mentioned, so they are independent, right? So because xk bar is the sample mean of the first k observations, okay, and the xk plus 1 is independent of the first k observations, so they are independent. Okay, so again, let's apply the result of the normal distribution. So the difference of the two independent normal random variables is also a normal distribution. Okay, so the mean will be the difference of the two means. Okay, and the variance equals the sum of the two variances. Right, so we have this. Okay, and again, we use the relationship between the normal and the chi-square distribution. Okay, so that is this normal. We standardized divided by its standard deviation. So then this follows the standard normal, right? And then the square of this standard normal distribution follows a chi-square 1 distribution. Okay, and then we can just take out this denominator. So then this constant part comes out of the square term. Okay, so this is exactly what we want to show. This follows the chi-square 1 distribution. Okay, so again, let's summarize the idea here. Okay, so here we want to show this this sample variance follows the chi-square n-1 distribution. Okay, and then what we use is the mathematical induction method. Okay, so that is we want to show when n equals 2. Okay, the S2 square follows the chi-square 1 distribution. So all those are involves the property of the normal distribution and the relationship of the chi-square with normal. Okay, so basically chi-square 1 is the square of the standard normal. Okay, so we have repeatedly used this property. Okay, so this is the first step for n equals 2. Okay, and for n equals k, so we assume this relationship is true. Then we need to show this is also true for n equals k plus 1. Okay, and then the key relationship is this inductive relationship between Sn squared and Sn minus 1 squared. Okay, so by using this inductory relationship, so we have this relationship when n equals k plus 1. Okay, so for the first term, we already show it is we already assume it is a chi-squared distribution. So the only thing is we need to show the second term also follows a chi-squared distribution, and it is independent of the first term. Okay, so again, we use to show the independent. So we repeatedly use the fact. So that is, if first those xi's are independent random variables. Okay, and the sample variance are functions of only the first k observations. Okay, so basically that is what we learned in chapter 4. Okay, functions of independent random variables are also independent. Okay, and to show this second term follows the chi-squared distribution. Okay, so again we repeatedly use the property of the normal distribution and its relationship with the chi-square distribution. Okay, so that is about this part. Okay, so the next part, okay, what we want to show in this, okay, so that is what is that? So that is the t distribution, So that is the ratio of this sample mean divided by this sample variance follows a t distribution. Okay, so here we write this in a more general way. So I would say this. Okay, so here we put the this after we put this n in the denominator, but we now put this in the numerator. Okay, and then we introduce this sigma square. Okay, so basically in the numerator we divided by this sigma. Okay, and we also divided the sigma square in the denominator. Okay, so we didn't change anything. Okay, so why we want to write this way? Okay, so here we just want to put this in a more general form. Okay, so here if we write the t statistic in this way, so here in the numerator, so that is a u here. The u here is just a standard normal random variable, right? So here in the numerator. Okay, and in the denominator, the v is a chi-squared distribution, right? So you can see this. Okay, the chi-squared distribution. So I will write the degrees of freedom p as n-1. Okay, so then to show this t statistic follows the t distribution. So what we want to show is here the u follows the standard normal distribution, and the v follows the chi-squared distribution with degrees of freedom is p as p. Okay, so then this form of the ratio of this form follows a t distribution. Okay, so here what we this is just for the t distribution f. I will just sketch the idea and leave the more detailed calculation in your homework. Okay, so here we just apply the Jacobian method. Okay, so here we already know u and v, so they are independent. So why is that? Okay, so because here t is a function of x bar, right? And v is a function of the sample variance s squared. And in the previous theorem, we have shown x bar and s squared are independent. So then their respective functions u and v are also independent. Okay, so if u and v are independent, so then we can directly write out the joint PDF of u and v. Right? So this joint PDF of u and v will be the product of the standard normal multiply the PDF of the chi-squared p. Okay, so then we have the joint PDF for u and v. Okay, so now to find out the PDF of t, so we want to show this t has a PDF as the student t distribution. Okay, so then we want to make this transformation. Okay, so here the the new variable t is just defined in as this ratio. Okay, and w, we will define w as the v. Okay, just one of the original random variables. Okay, and the rest part is just we use the Jacobian method to do the transformation to find out the joint PDF of t and w. Okay, so then we can, based on this transformation, so we can solve for u and v. Okay, and then now we just plug in, we can also calculate the Jacobian. Okay, and then we can plug in this solution for u and v into the joint PDF. Okay, now we can find the joint PDF of t and w. Okay, this joint PDF of u and v multiply the Jacobian. Okay, and the last step is we need to find out the marginal distribution of t. So we need to integrate out w. Okay. Okay, so I think here the idea is clear, right? So first we write this ratio as a independent standard normal and chi-squared random variables. Okay, so then we can write out the joint PDF of u and v. And then we make the transformation and apply the Jacobian method to find out the joint PDF of T and W, and then integrate out W to find out the joint PDF of T. Okay, so that is the idea. So you will see after you finish all the calculation, so you can compare the PDF of T, okay, with the form of PDF in the of the student T distribution. So you will see they are the same. Okay, so then this statistic T statistic follows the T distribution. Okay, so that's the idea. Okay, so next one, the derivation of the F distribution. The F distribution. Okay, so here we use the similar idea as the T distribution. Okay, so here we write this ratio. Again, we use the U and the V to denote two chi-squared random variables. Okay, so one follows the this degrees of freedom P. Okay, second, in the denominator, the V follows the chi-squared distribution with degrees of freedom Q. Okay, so which is here. Okay, so now here the U and the V, so they are independent. They are from the independent normal distributions X and Y. So they are also independent. Okay, and again, so we can write out the joint PDF of U and V. So which are the product of two independent chi-squared PDFs. Okay, so we can get the PDF of the joint PDF of U and V. Okay, so again, now we want to find this distribution of X, so which is the ratio of U and V in this way. Okay, so now we want to make this transformation. So X is the ratio. Okay, and the Y here is we just make this Y as U plus V. Okay, this way can simplify the calculation a little bit. Okay, because here in the joint PDF of U and V, so we have the essential term is a sum of U and V. Okay, so then we will make this transformation to simplify the calculation. Okay, but you can also make the Y equals to 1 of U and V. Okay, the only thing is the calculation is a little bit complicated. Okay, and for the rest part, so again, we just apply the Jacobian method, to find out the U and V, solve for U and V in terms of X and Y. Okay, and calculate the Jacobian. Okay, and then apply this Jacobian method to find out the joint PDF of X and Y. And the last step is to integrate out Y to find the marginal PDF of X. Okay, and then if you finish the calculation, so you will see this is exactly the form of the PDF of F distribution. Okay, so then this is the idea here, how to derive the T distribution and the F distribution. Okay. Okay, so far we have finished all the materials. Okay, so a few words about this this part. Okay, so as I mentioned, so those T distribution and derivation of T distribution and F distribution. So I will leave the calculation in your homework. Okay, so those derivation and calculations are required in the exam. Okay, and I can tell you there will be questions, okay, related to the T distribution and the F distribution. Okay, they more precisely, they will be the same, exactly the same things I mentioned here. Okay, I will leave the details in your homework. Okay, so I can tell they will appear in your final exam. Okay, so that is the requirements for this part. Okay, so far we have finished all the materials for this semester. Okay, I want to thank you very much, for tolerating me, okay, during the whole semester. Okay, and I do hope you have learned useful things from this course, so which provide you kind of the theoretical basis for your future study in statistics. Okay, and we have by working together, we have passed this difficult time of this pandemic period. Okay, I'm glad we have finished all the required materials. Okay, thank you very much. Okay. Oh, okay. One more thing. Okay, I will also be here, throughout the Thanksgiving holiday and to our final exam. Okay, so if you have any questions, okay, so please, either email me or contact me in either way, and we can schedule time, to discuss your questions. Okay, and I will upload all those materials onto D2L, including the video lectures, the last 2 recorded video lectures. Okay, so any other questions? Let's see. No question. Okay, no questions. Okay. So then I wish you a great Thanksgiving holiday, and we will see each other on the exam day. Okay. Enjoy the holiday and good luck. Okay, thank you very much. Okay, thank you very much, everyone. Okay, bye.